Welcome to This Explainer. Today, we're diving straight into the fascinating underlying engine that is literally powering the modern AI revolution. If you've used any kind of modern AI chatbot or image generator recently, you've interacted with this exact technology. But to really understand it, I want to kick things off by posing a very simple, maybe even a little bit obvious, mystery.
We hear this acronym constantly, right? ChatGPT. It's everywhere. We generally know the chat part, and GP stands for generative pre-trained, which just tells us a bit about how the model was trained. But what about that final crucial letter? What does the T actually stand for?
Well, spoiler alert, the T stands for transformer. And no, we are definitely not talking about those gray metal cylinders you see up on electrical poles. And we aren't talking about giant robotic action figures from the movies either. In the world of artificial intelligence and deep learning, a transformer is a very specific type of neural network architecture. Its absolute superpower is its ability to process sequential data. That could be human language, music, or even computer code, all at once. By doing this, it learns the deep context and tracks the incredibly intricate relationships between every single piece of that data.
It's kind of crazy to think about, but this entire paradigm shift started with just one single document. Back in 2017, a team of researchers at Google published a seminal paper, and it had a surprisingly catchy title, "Attention is All You Need." Before this paper came out, the most advanced AI models out there relied on highly complex structures with all sorts of convolutions and recurrent loops. Well, this 2017 paper proposed throwing all of that away. They introduced the transformer architecture, proving that you could actually achieve vastly superior results using a much simpler mechanism. And the whole thing relied entirely on a concept called attention.
Section 1, the secret sauce, self-attention. Let's get right into the absolute core mechanism of the transformer architecture.
Consider a sentence like this. The animal didn't cross the street because it was too tired. Now for you and me, reading this is completely effortless. We instantly, intuitively know that the word "it" refers to the animal, not the street, right? Because streets obviously don't get tired. But for a machine, this is a massive, highly complicated puzzle. How does a computer algorithm, which literally only understands pure math, figure out what "it" is referring to? This is the exact problem that earlier AI really struggled with, and it's exactly what the transformer finally solves.
So how exactly does it solve this pronoun puzzle? Transformers use a clever mechanism called self-attention. When the model processes the word "it," self-attention doesn't just put blinders on and look at it in total isolation. Instead, it looks at every single word in that entire sentence simultaneously. It acts a lot like a giant scoring system. The model calculates mathematical scores that represent the relationship between it and every other word around it. It quickly realizes there's a super strong contextual link to animal because, again, animals get tired, so it assigns animal a very high attention weight. At the exact same time, it gives irrelevant words like street a tiny, almost non-existent score, effectively drowning them out. In doing this, it physically bakes the meaning of animal right into its mathematical representation of the word "it."
To really understand how this calculation works under the hood, think of it like being at a super loud, packed cocktail party. Your brain naturally focuses on the single voice of the person you're actually talking to, naturally filtering out all that background noise. The transformer does this using three specific vectors: queries, keys, and values. Imagine each word is actively asking a question. That's its query. Meanwhile, every other word is holding up a little tag explaining what information it has to offer. That's its key. Now, if a query and a key are a good match, kind of like a physical lock and key clicking together, the model grabs the value, which is the actual contextual information, and passes it right along. This brilliant filtering mechanism is exactly how the AI navigates complex, long-distance relationships in text.
Section 2, transformers versus older tech. So we know how the model focuses, but why did this specific setup completely take over the industry?
Before 2017, the absolute gold standard in AI was something called recurrent neural networks, or RNNs. But RNNs have a major flaw. They process text sequentially, kind of like an old-school factory assembly line. They read word 1, then word 2, then word 3. As you can imagine, this is incredibly slow, creating a massive computational bottleneck. Plus, by the time an RNN gets to the end of a long paragraph, it often literally forgets what the first sentence was even about. Transformers change the whole game by utilizing parallel processing. Because of self-attention, they can ingest and process the entire sequence of data all at exactly the same time. No more waiting in line. This means they train lightning fast, they can take full advantage of modern graphics processing units, and they absolutely never lose the context of a long document.
Section 3. Architecture blocks, encoders and decoders. When you hear about different AI models in the news, they are usually just different arrangements of these two foundational pieces.
You can think of the transformer as a highly modular architecture, almost like digital Lego blocks. First up, we have encoder-only models. An encoder's whole job is to read and build a deep mathematical understanding of the input. Google's BERT is a famous example here. It's phenomenally good at understanding context, which is exactly why it revolutionized Google search. Next, we have decoder-only models. A decoder is optimized for actually generating outputs, predicting the next word one step at a time. The entire GPT family, which, yes, powers ChatGPT, is built entirely out of stacked decoders. And finally, you can stack them together into an encoder-decoder architecture, like Google's T5 model. In this setup, the encoder reads the input, say a full sentence in English, and passes its deep understanding directly to the decoder, which then generates the output, say the perfect translation in French.
Section 4. In action, next word prediction. Now that we have all the puzzle pieces on the table, let's walk through what actually happens when you type a prompt.
Let's look at the step-by-step journey of next word prediction in a decoder model. Step 1 is tokenization. The AI takes your input text and breaks it down into numerical tokens, because remember, machines only speak math. Step 2 is absolutely crucial, positional encoding. Remember how we just said transformers process everything in parallel all at once? Well, because of that, they inherently have no concept of word order. To fix this glaring issue, the model adds a mathematical stamp to each token, often using sine and cosine functions, so the AI knows exactly where each word sits in the sentence. Step 3 is the self-attention mechanism we just talked about, where it uses queries, keys, and values to score relationships and build context. Finally, step 4 is the output. The model passes this incredibly rich contextual data through a final feed-forward network to calculate probabilities. It looks at its entire vocabulary and predicts the single most likely next word. Then, it feeds that brand new word back into itself, and the cycle repeats, autoregressively, writing a full essay for you right before your eyes.
And finally, Section 5, Beyond Words, New Frontiers. This architecture is considered a massive revolution because, as it turns out, it's not just about language anymore.
Because transformers treat data as a sequence, researchers quickly realized they could apply this architecture to almost anything. Just look at some of these new frontiers. By treating image pixels as a sequence, vision transformers are now totally outperforming older computer vision models, combining NLP and vision to generate incredible AI art. In the world of biology, scientists are treating segments of DNA just like sentences in a book. Transformers are actually learning the grammar of genetics to predict mutations. They are even decoding the long chains of amino acids in proteins, figuring out how they fold in 3D space, which is unlocking massive, real-world breakthroughs in drug discovery. Even in robotics, we are seeing decision transformers treat a robot's physical actions over time as a sequence, helping machines learn to navigate the real world.
We've moved from literally just predicting the next word on a screen to predicting the fundamental building blocks of life and reality. This architecture, which was born from a simple desire to improve machine translation back in 2017, is now a general-purpose engine for understanding our world. So I want to leave you with this final thought. If a transformer can so elegantly decode the language of biology, vision, and robotics, what sequence will it master next?
If you enjoyed this video, please like, comment, and subscribe for more AI and technology content. Thanks for watching.